Imagine discovering that planets don't grow naturally, they're planted. For decades, scientists puzzled over how gas giants form so quickly around distant stars. Then came 3I-ATLAS, drifting in from the void with a chemical signature that reads like a cosmic instruction manual. This interstellar wanderer carries the exact materials needed to jumpstart planetary formation, almost as if designed for the task. But there's something else aboard this celestial seed that makes even skeptical astronomers wonder, could something actually be alive inside? The evidence we've gathered suggests three possibilities, each more extraordinary than the last. From dormant microbes to living technology, from natural seeding to deliberate gardening, the truth about 3I-ATLAS will redefine our place in the galaxy. By the end of this late-night exploration, you'll understand why this peculiar object might hold the key to our understanding of the cosmos. Part 1 is 3I-ATLAS alive? Could something be alive inside 3I-ATLAS, or is the object itself a planet seed? Three roads stretch before us like paths through an alien forest. The first, a natural comet, albeit one with peculiar chemistry that defies our expectations. The second, an engineered artifact, carefully disguised as cosmic debris. The third, a biological or living seed, carrying the blueprints for worlds yet unborn. We will test each against the mounting evidence, then follow where the data leads us, even if it challenges everything we thought we knew about how planets form. Let us establish the basics swiftly. 3I-ATLAS stands as the third confirmed interstellar object ever discovered by humanity. The ATLAS survey team in Rio Hurtado, Chile, spotted it on July 1st, 2025. This wanderer travels on a hyperbolic path, unbound by our sun's gravitational embrace, confirming its interstellar origins. Fortunately for Earth's inhabitants, it poses no threat whatsoever. Its closest approach brings it within roughly 1.8 astronomical units of our world on December 19th, 2025. But here lies our first tantalizing clue. The timeline itself reads like a carefully choreographed celestial dance. October 3rd, 2025 marks its near-Mars passage at approximately 30 million kilometers. October 29th brings perihelion, its closest solar approach at 1.36 astronomical units, conveniently positioned behind the Sun from Earth's perspective. March 16th, 2026 delivers the grand finale, a near-Jupiter encounter at just 0.36 astronomical units. These waypoints offer multiple spacecraft an unprecedented opportunity to observe. Mars orbiters stand ready, potential Jupiter system assets await their moment. The cosmic clockwork appears almost too perfect, too convenient, a thought that will resurface as our investigation unfolds. Now, consider the mounting anomalies that refuse to fit neatly into our comet taxonomy. A carbon dioxide dominant gas coma emerges, where water vapor typically reigns supreme. Early hydroxyl activity, the signature of water dissociation, appears far from the Sun's warming embrace, defying conventional wisdom about cometary awakening. A sun-facing dust plume creates what some call a forward glow, challenging expectations of how cosmic debris should behave. Perhaps most intriguingly, spectroscopic analysis reveals nickel signatures, while iron lines remain frustratingly weak or undetected entirely. The polarization behavior of scattered light tells its own strange story, refusing to match the fingerprints of familiar solar system comets. Each anomaly stands alone as merely curious. Together, they form a pattern that demands explanation. This is not just another comet drifting through our cosmic neighborhood. If natural, 3I-ATLAS reshapes our understanding of how and where comets form in the frigid reaches between stars. If it represents a planet seed, a ready-made core awaiting capture by a young stellar system, it rewrites the timeline of planetary formation itself. If artificial, if engineered, if deliberately sent, then we stand at the threshold of history's most momentous discovery. We promise a fair test, separating measured facts from speculation clearly marked as such. The scientific community harbors deep skepticism toward extraordinary claims, and rightfully so. Expert pushback will receive its due consideration alongside the anomalous observations. Understanding what interstellar truly means requires grasping the physics of cosmic wanderers, These objects carry high velocities relative to local stellar motion, following hyperbolic trajectories with eccentricities far exceeding 1. Most interstellar visitors pass through our solar system unnoticed, detected only after they have already departed, if at all. The early discovery of 3I-ATLAS changes everything. Months of coordinated observation campaigns now unfold across humanity's greatest instruments. The Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories worldwide, and assets stationed throughout our solar system. Never before have we possessed such comprehensive surveillance of an interstellar intruder. If 3I-ATLAS represents a seed, a cosmic gardening tool evolved by nature or designed by intelligence, what might it be seeding? Could seeds carry the chemical ingredients for life? Could they transport life itself, dormant passengers awaiting resurrection in the warm embrace of a young stellar system? The implications stretch across disciplines. Biology meets astronomy. Planetary science encounters questions of design and intention. The search for extraterrestrial intelligence suddenly finds itself examining not radio signals from distant civilizations, but a possible artifact drifting through our own backyard. By this investigation's end, 3 plausible endings will emerge from the evidence. You, the jury, will weigh the testimony and choose which explanation best fits the facts. Will you conclude that nature alone crafted this interstellar wanderer? Will you embrace the radical notion of cosmic seeding, whether natural or artificial? Or will you find yourself confronting the extraordinary possibility that intelligence has come calling, wearing the mask of a simple comet? The clock ticks toward our first major observational milestone. Mars awaits its close encounter in mere weeks. Behind the Sun, perihelion approaches like a curtained stage where the real performance may finally begin. The evidence mounts, the theories compete, and somewhere in the darkness between stars, other wanderers drift toward appointments with destiny we cannot yet imagine. But first, we must examine the loudest claim echoing through scientific corridors and social media alike, the hypothesis that refuses to whisper when it might instead shout its defiance of conventional wisdom. Part 2. The Alien Hypothesis. The alien hypothesis arrives not with subtle whispers, but with the confident proclamations of Harvard's Abraham Loeb, a respected astrophysicist whose previous work on black holes and cosmic structure commands academic respect. Yet his interpretation of 3I-ATLAS has ignited fierce debate across the scientific community. Loeb presents his case with mathematical precision. He highlights the object's unusually tight alignment with our solar system's planetary plane. Retrograde motion, yes, but tilted only approximately 5 degrees off the ecliptic. Most interstellar visitors arrive from random directions, their trajectories reflecting the chaotic dynamics of stellar encounters. 3I-ATLAS appears almost domesticated by comparison, as if following familiar orbital highways. The sequential planetary encounters trouble Loeb most profoundly. Mars, then Venus at greater distance, then Earth's remote vicinity, finally Jupiter's doorstep, a cosmic itinerary that reads like a reconnaissance mission crafted by patient intelligence. He calculates the probability of such an alignment occurring purely by chance at roughly 0.005% under his assumptions. This represents his interpretation, not peer-reviewed consensus, but the mathematical framework demands serious consideration. The forward glow phenomenon provides Loeb's second pillar of evidence. He emphasizes the object's sunward, cigar-like brightness profile, an illumination pattern that strikes him as deeply suspicious. However, Hubble Space Telescope analysis reveals a more nuanced picture, a sun-facing dust plume driven by heating, accompanied by a faint anti-solar tail extending in the opposite direction. Comet-like physics can indeed produce sunward brightness fans through asymmetric outgassing and dust ejection patterns. Here we must separate peer-reviewed observations from speculative interpretations. The sunward brightness exists. Multiple telescopes confirm this reality. Whether it represents natural physics or artificial design remains hotly contested. The nickel detection story grows more complex under scrutiny. The Very Large Telescope's ultraviolet and visual Echelle spectrograph detected neutral nickel emission lines, while ion signatures remained absent in those particular spectra. Loeb and others suggest this pattern might indicate processed metals, alloys refined by industrial processes rather than cosmic chemistry. Yet non-detection does not equal zero abundance. Iron may exist below detection thresholds, or excitation conditions may favour nickel emission over iron. Previous comets have exhibited nickel signatures without raising eyebrows about extraterrestrial manufacturing. The leap from unusual metal ratios to industrial origin requires extraordinary justification. Loeb ventures into darker speculation with his dark forest scenario, borrowed from science fiction but applied to real astronomical data. If 3I-ATLAS represents a reconnaissance probe, scheduling perihelion passage behind the Sun would minimize Earth-based observation opportunities. The timing appears conveniently opaque from our perspective. This interpretation assumes intentional design, deliberate concealment, strategic thinking applied to orbital mechanics. No evidence of course corrections or maneuvering exists in current datasets, but Loeb argues that advanced technology might operate below our detection thresholds. The writings of Loeb, along with collaborators Hibbard and Crowell, explore scenarios ranging from passive observation to possibly hostile intentions. They speculate about probe capabilities, data collection objectives, even potential threats to human civilization. The scientific community has responded with fierce criticism, labeling such speculation as nonsense and unsubstantiated fear-mongering. The pushback reflects deeper tensions within astronomy itself. How far should scientists venture into speculative territory? When does healthy skepticism become closed-minded orthodoxy? When does open inquiry become irresponsible sensationalism? Genuine technosignatures would require specific observational criteria. Persistent non-gravitational accelerations, inconsistent with sublimation physics, would raise immediate red flags. Artificial light curves, brightness variations following programmed rather than rotational patterns, might indicate active systems. Structured, repeating jet emissions could suggest attitude control or deliberate signaling. Narrowband radio or optical emissions would scream artificial origin to any astronomer. So far, none of these smoking guns have emerged from the data. 3I-ATLAS behaves remarkably like a comet, albeit an unusual one, in every measurable parameter. It outgasses, develops a coma, exhibits dust emission patterns consistent with solar heating, and follows gravitational mechanics precisely. The alien hypothesis faces its greatest challenge in the burden of extraordinary proof. Carl Sagan's famous maxim applies with full force. Extraordinary claims require extraordinary evidence. Loeb's mathematical arguments about trajectory probabilities, while interesting, do not constitute proof of artificial origin. Statistical improbability alone cannot distinguish design from natural coincidence, especially when dealing with single events rather than reproducible patterns. The broader scientific community remains deeply skeptical, and their caution serves important purposes. False positive declarations of extraterrestrial technology would damage public trust in astronomy and SETI research for decades. The community learned hard lessons from the premature excitement surrounding pulsars, fast radio bursts, and other phenomena that initially seemed impossibly artificial. Yet Loeb's persistence has generated valuable scientific activity. His hypothesis, however controversial, has motivated detailed observational campaigns, encouraged new analytical techniques, and forced the community to articulate exactly what evidence would constitute proof of artificial origin. Even incorrect hypotheses can advance knowledge by sharpening our investigative tools. The alien interpretation also highlights our profound ignorance about interstellar object populations. We have observed exactly 3 confirmed examples: 1I/Oumuamua, 2I/Borisov, and now 3I-ATLAS drawing. Broad conclusions from such a tiny sample size invites error. What seems anomalous today might prove commonplace tomorrow as our census expands. The philosophical implications loom larger than the technical disputes. If confirmed artificial, 3I-ATLAS would instantly become the most important discovery in human history. Every assumption about our cosmic isolation would crumble. Every SETI strategy would require fundamental revision. Every planetary defense protocol would face urgent updating. But confirmation remains elusive, frustratingly out of reach, despite months of intensive observation. The evidence points consistently toward natural origin, even if the specific chemistry and physics prove more exotic than typical solar system comets. As we move forward, the alien hypothesis serves as one crucial benchmark against which to measure all observations. Every anomaly receives scrutiny through this lens. Every new dataset undergoes analysis for potential technosignatures. The hypothesis may ultimately fail. Most scientists expect exactly this outcome, but its failure will rest on evidence rather than dismissal. Next, we must examine what the measured activity patterns actually reveal about 3I-ATLAS. The object's behavior tells a story, but which story depends on how we interpret the increasingly complex evidence streaming back from our telescopes and spacecraft. Part 3. The evidence of activity. The Swift Observatory's ultraviolet, divided by optical telescope, delivered the first shock to conventional comet wisdom. Hydroxyl emissions, the telltale signature of water vapor dissociation, appeared around 3.5 astronomical units from the sunday. This distance places the detection far beyond the traditional activation zone, where solar heating typically awakens cometary volatiles. To appreciate this anomaly's significance, consider that most solar system comets remain dormant until approaching roughly 3 astronomical units. 3I-ATLAS began venting water well before reaching this threshold, suggesting either unusual composition or exotic sublimation physics. The early water activity hints at a porous, volatile-rich interior, responding to even modest solar warming. The James Webb Space Telescope's near-infrared spectrograph team delivered an even more startling revelation. Their analysis reveals a carbon dioxide to water ratio of approximately 8:1, dramatically skewed toward carbon dioxide compared to typical solar system comets. This composition profile places 3I-ATLAS in uncharted chemical territory. Most familiar comets exhibit water dominance, with carbon dioxide playing a supporting role. The reversed ratio suggests formation in environments far colder and more carbon dioxide rich than the regions where our solar system's comets originated. Perhaps 3I-ATLAS condensed in the outer reaches of a different stellar system, where carbon dioxide could freeze out preferentially over water ice. Alternatively, the unusual chemistry might reflect thermal processing during its interstellar journey. Cosmic ray bombardment and stellar encounters could alter surface composition over geological timescales. The specific mechanisms remain unclear, but the chemical fingerprint definitely marks 3I-ATLAS as chemically distinct from local comet populations. Cyanogen emission lines strengthen the active comet interpretation while adding another puzzle piece to the chemical inventory. CN emissions typically correlate with organic compound sublimation, suggesting 3I-ATLAS carries complex carbon-nitrogen chemistry within its nucleus. This detection helps astronomers locate chemical boundaries as the object approaches the Sun, providing crucial constraints on sublimation physics. The polarimetry measurements reveal perhaps the most intriguing anomaly yet discovered. Early observations show an unusually strong and extended negative polarization branch, light scattering in ways that differ markedly from most solar system comets. This optical behavior suggests dust grains with exotic properties, unusual size distributions, porosity levels, or compositional differences that affect how sunlight interacts with the coma material. Polarimetry serves as a sensitive probe of dust physics. The way particles scatter light depends intimately on their size, shape, composition, and internal structure. 3I-ATLAS produces polarization signatures that do not match any clear category in our existing comet taxonomy, hinting at formation processes or evolutionary histories unlike anything in our local experience. The Hubble Space Telescope resolved the forward glow mystery with characteristic precision. High-resolution imaging reveals a dust plume extending from the sun-facing hemisphere, driven by asymmetric heating and outgassing. Additionally, a faint tail stretches in the anti-solar direction, exactly as expected for natural comet behavior. This observation deflates some of the more exotic interpretations of the forward brightness. Solar heating naturally creates temperature gradients across rotating bodies, leading to preferential outgassing from warmer surfaces. The resulting dust patterns can indeed create forward-directed brightness enhancements without requiring artificial explanations. Size constraints from Hubble impose important limits on speculation. The nucleus diameter appears to span roughly 0.44 to 5.6 kilometers nowhere, near the Manhattan-sized descriptions that proliferated in early media coverage. This relatively modest size scale eliminates certain categories of exotic hypotheses, while fitting comfortably within expected parameters for interstellar wanderers. Measuring accurate sizes proves challenging when active comas swamp the nucleus signal. Hubble's resolution reaches its limits even with careful image processing and multiple observation epochs. The current size estimates carry substantial uncertainties, but they establish reasonable bounds for theoretical modelling and comparison with other interstellar objects. The cumulative activity pattern resembles comet behaviour in fundamental ways, while exhibiting chemical and physical anomalies that distinguish 3I-ATLAS from typical solar system examples. This combination of familiar physics with exotic composition creates an interpretive challenge for astronomers attempting to classify the object. What observational evidence would definitively separate natural from artificial origins? Persistent thrust-like accelerations, inconsistent with sublimation models, would immediately trigger artificial hypotheses. Such accelerations would appear as systematic deviations from pure gravitational trajectories, potentially observable through precise astrometric monitoring over extended periods. Engineered spectral features represent another potential smoking gun. Narrow-band emissions at frequencies associated with specific technologies or elemental ratios, impossible to achieve through natural processes, would demand artificial explanations. However, defining impossible ratios requires comprehensive understanding of interstellar chemistry, knowledge we currently lack. Temporal patterns in outgassing could reveal artificial control systems. Natural sublimation follows predictable temperature-driven cycles tied to solar heating and rotation periods. Artificial jets might exhibit timing patterns disconnected from these natural rhythms, suggesting active control over volatile release mechanisms. So far, none of these decisive signatures have emerged from the data. 3I-ATLAS continues behaving like a chemically unusual but fundamentally natural comet. Its anomalies intrigue without convincing, challenge without conclusively overturning conventional interpretations. The absence of clear technosignatures does not eliminate artificial hypotheses entirely. Advanced technology might operate below current detection thresholds, or we might lack the conceptual frameworks necessary to recognize truly alien engineering. However, the burden of proof remains squarely on extraordinary claims, requiring extraordinary evidence. The chemical anomalies do raise profound questions about interstellar object diversity and formation processes. If 3I-ATLAS represents typical interstellar comet chemistry, our theories of outer system volatile evolution require significant revision. The carbon dioxide dominance and early water activity suggest formation environments substantially different from our solar system's comet-forming regions. These chemical differences could trace back to the parent stellar system's formation history, subsequent evolution, and ejection mechanisms. Different stars form from molecular clouds with varying compositions. Different planetary systems experience distinct dynamical histories. The specific combination of factors that produced and ejected 3I-ATLAS might be rare or commonplace. We simply lack sufficient data to judge. As our investigation continues, the evidence of activity provides crucial constraints on theoretical models while raising new questions about cosmic chemistry and physics. The object clearly belongs to the active comet category, but it stretches this classification in unexpected directions. What could alive inside possibly mean for such an object? The question demands careful definition before we can evaluate its plausibility against the mounting evidence. Part 4. What alive inside could mean. When we speak of something being alive inside 3I-ATLAS, we must navigate carefully through three distinct conceptual territories. Each represents a different interpretation of what life might mean in the context of an interstellar wanderer. The first notion embraces literal biology, microbial life forms existing within the object's core, protected by layers of ice and dust from the harsh radiation environment of interstellar space. This scenario demands organisms capable of surviving not just freezing temperatures, but also cosmic ray bombardment, vacuum conditions, and potentially millions of years in dormancy. Earth provides tantalizing examples of such resilience. Extremophile bacteria thrive in conditions once thought impossible for life. Deep ocean thermal vents, highly radioactive environments, Antarctica's buried lakes, and even the vacuum of low Earth orbit. Some species enter cryptobiotic states, suspended animation lasting decades or longer, then resume normal biological activity when conditions improve. The shielding provided by ice and dust layers could theoretically protect interior microbes from lethal radiation doses. Calculations suggest that several meters of frozen material might reduce cosmic ray exposure to biologically tolerable levels. During warmer passages near stars, heating could potentially create temporary liquid water zones within the porous interior, awakening dormant biology for brief active periods. This biological scenario remains purely speculative, lacking any direct observational evidence. Yet the physics appears marginally plausible under carefully constrained conditions. The key questions revolve around initial contamination mechanisms, survival timescales, and detection possibilities. The second interpretation ventures into biotechnology territory, self-repairing materials or systems that blur the boundary between living organisms and engineered devices. This living technology concept draws inspiration from emerging fields like synthetic biology and programmable matter. Imagine materials that respond to environmental changes, repair damage automatically, or modify their properties according to programmed objectives. Such systems might incorporate biological components within technological frameworks, creating hybrids that exhibit lifelike behaviors without being strictly alive in traditional biological senses. Applied to 3I-ATLAS, this interpretation might explain seemingly deliberate outgassing patterns or adaptive responses to solar heating. The object could theoretically contain self-modifying systems designed to optimize performance across varying environmental conditions encountered during interstellar journeys. Again, no observational evidence supports such exotic explanations. The concept remains firmly planted in speculative territory, though advancing terrestrial biotechnology makes such possibilities increasingly conceivable for sufficiently advanced civilizations. The third notion embraces full artificiality, a spacecraft or probe deliberately disguised as a natural comet. This scenario requires sophisticated engineering capable of mimicking comet behavior while concealing technological signatures from astronomical observation. Creating a convincing comet disguise would demand detailed understanding of sublimation physics, dust production mechanisms, and spectroscopic signatures. The camouflage would need to function across multiple wavelengths and observation techniques, while maintaining the illusion of natural behavior. Such deception might serve reconnaissance purposes, allowing detailed study of stellar systems without triggering defensive responses from potentially hostile civilizations. The dark forest hypothesis suggests that cosmic survival might depend on remaining undetected by more advanced species. The nickel detection without corresponding iron signatures has sparked in particular speculation along these lines. Some researchers wonder whether selective metal ratios might indicate industrial processing rather than natural cosmic chemistry. However, the absence of iron lines in specific spectral observations does not prove zero iron abundance. Excitation conditions, abundance ratios, and detection sensitivities all influence which elements appear prominently in spectra. Nickel emission has been observed in previous comets without suggesting artificial origins. The interpretive leap from unusual metal ratios to industrial processing requires much stronger evidence than currently available. The sunward dust plume, while striking, admits natural explanations through asymmetric heating and rotation effects. Solar radiation creates temperature gradients across object surfaces, driving preferential outgassing from warmer regions. The resulting dust patterns can create forward-directed brightness enhancements that might appear artificial to casual observers. Regarding habitability within 3I-ATLAS, the physical conditions present formidable challenges for biological activity. Internal temperatures likely remain well below freezing throughout most of its trajectory. Brief warming periods near stellar encounters might create transient liquid zones, but these would persist for relatively short timescales. The more plausible scenario involves organic chemistry processing rather than thriving ecosystems. Complex carbon compounds could undergo slow transformation reactions during extended dormancy periods, potentially creating chemical conditions favourable for life if and when liquid water becomes available. The concept of living technology raises fascinating questions about the boundaries between life and artifact. If we discovered materials that grew, reproduced, adapted, and responded to environmental challenges, would we classify them as biological or technological? The distinction might prove meaningless for sufficiently advanced engineering approaches. Programmable matter represents one terrestrial research direction that could eventually blur these boundaries. Materials designed to reconfigure themselves according to programmed instructions might exhibit behaviors indistinguishable from biological growth or adaptation. Applied to interstellar exploration, such capabilities could enable remarkable versatility. Probes might adapt their configurations for different mission phases, repair damage automatically, or modify their behavior based on discovered conditions in target systems. The burden of proof for any alive inside hypothesis remains extraordinarily high. Claims of biology, biotechnology, or sophisticated artificiality require evidence that current observations cannot provide. Speculation serves valuable purposes, expanding conceptual horizons, motivating new observation strategies, exploring theoretical possibilities, but speculation alone cannot establish truth. What specific evidence would support biological hypotheses? Detectable metabolic byproducts, complex organic signatures inconsistent with abiotic chemistry, or isotopic ratios, indicating biological processing might provide compelling clues. However, distinguishing biological from abiotic organic chemistry proves notoriously difficult even for terrestrial samples. Technological hypotheses would require more obvious signatures. Narrowband emissions, systematic trajectory modifications inconsistent with natural physics, or spectral features impossible to produce through known cosmic chemistry. Advanced camouflage might conceal such signatures, but invoking undetectable technology approaches unfalsifiable speculation. The philosophical implications of any confirmed alive inside scenario would dwarf the technical discovery itself. Biology would suggest either natural panspermia or deliberate seeding of stellar systems. Technology would imply observation, possibly evaluation, potentially contact preparation. Either discovery would revolutionize our understanding of life's cosmic distribution and intelligence's prevalence throughout the galaxy. The implications for human civilization, planetary defense strategies, and our species' cosmic perspective would prove profound beyond current imagination. Yet, extraordinary claims demand extraordinary evidence, and current observations fall far short of supporting such revolutionary conclusions. 3I-ATLAS behaves consistently with natural comet physics, even if its specific chemistry proves more exotic than typical solar system examples. As we continue investigating, the alive inside concepts serve as important benchmarks for evaluating evidence. They remind us to remain open to unexpected possibilities while maintaining rigorous standards for proof. The universe has surprised us repeatedly throughout scientific history, but surprise requires solid evidence, not merely interesting speculation. A different radical idea has begun gaining traction within mainstream astronomical circles, offering natural explanations for cosmic seeding processes that require no biology or technology whatsoever. Part 5. Pushback from mainstream science. The National Aeronautics and Space Administration classifies 3I-ATLAS unambiguously as an active comet. Period. Full stop. No official agency endorses alien technology claims, artificial origin hypotheses, or living spacecraft speculation. This institutional position reflects decades of hard-earned wisdom about distinguishing genuine discoveries from sensationalized misinterpretations. Leading comet researchers have responded to extraordinary claims with characteristic scientific caution. Darrell Seligman, at the University of Chicago, advocates evidence-first approaches, emphasizing the importance of exhausting natural explanations before invoking exotic alternatives. Robert Lawler from the Planetary Science Institute echoes this sentiment, noting that unusual chemistry does not automatically imply artificial origin. Marco Micheli from the European Space Agency stresses the need for reproducible observations before drawing revolutionary conclusions. These experts understand that the history of astronomy contains numerous examples of premature excitement over seemingly impossible phenomena. Pulsars initially appeared so artificial that researchers briefly considered extraterrestrial beacon hypotheses. Fast radio bursts seemed impossibly energetic until natural mechanisms emerged from theoretical work. Tabby's star exhibited bizarre dimming patterns that sparked alien megastructure speculation before dust cloud explanations gained acceptance. The pattern repeats consistently. Anomalous observations generate exotic hypotheses until patient investigation reveals natural mechanisms previously unknown to science. This historical precedent motivates conservative approaches to interpreting 3I-ATLAS data. The probability arguments central to artificial origin claims face methodological criticism from statistics experts. Post hoc probability calculations, analyzing odds after observing specific outcomes, suffer from selection bias and cherry-picked assumptions. When dealing with single events rather than reproducible experiments, distinguishing genuine anomalies from random fluctuations becomes notoriously difficult. Consider the trajectory alignment that some find suspicious. Critics note that any specific orbital configuration will appear improbable when calculated after the fact. The question is not whether this particular trajectory seems unlikely, but whether it represents a meaningful deviation from expected interstellar object behavior, given our extremely limited sample size. With only 3 confirmed interstellar objects observed by humanity, drawing broad statistical conclusions about typical versus atypical behavior invites error. What appears anomalous today might prove commonplace tomorrow as our census expands through surveys, like the Vera Rubin Observatory's legacy survey of space and time. Regarding non-gravitational accelerations that might indicate artificial propulsion, current measurements show nothing anomalous beyond experimental uncertainties. The tiny forces expected from comet outgassing could easily remain below detection thresholds, given present astrometric precision limits. Natural comets exhibit non-gravitational accelerations routinely as sublimating volatiles create rocket-like thrust effects. These forces follow predictable patterns related to solar heating, rotation periods, and volatile distribution. Detecting artificial thrust requires demonstrating systematic deviations from these natural acceleration patterns, evidence that remains elusive for 3I-ATLAS. The nickel emission without corresponding ion detection has generated considerable discussion, but comet chemistry experts note that this pattern does not necessarily indicate industrial processing. Different elements exhibit varying excitation thresholds and emission line strengths under specific physical conditions. Nickel has appeared in previous comet spectra without triggering artificial origin hypotheses. The transition metals present in cosmic dust often display selective emission patterns depending on temperature, density, and radiation field characteristics. Absence of ion lines, in particular observations, cannot be interpreted as proof of metallurgical refinement. Furthermore, the analytical challenges of extracting accurate abundance ratios from spectroscopic data of active comets should not be underestimated. Dust clouds, varying excitation conditions, and contamination from multiple emission regions complicate quantitative interpretation. What appears to be missing iron might reflect observational limitations rather than genuine absence. The polarimetry anomalies that seem to distinguish 3I-ATLAS from solar system comets admit natural explanations through exotic dust physics, rather than artificial engineering. Interstellar environments subject particles to different processing mechanisms compared to local solar system conditions. Cosmic ray bombardment, stellar wind interactions, and thermal cycling during extended interstellar journeys could produce dust grains with unusual optical properties. Size distributions, porosity levels, and compositional modifications might create polarization signatures, unlike anything observed in comets formed and evolved within our solar system. Scientific conservatism serves crucial protective functions for astronomical research credibility. False positive declarations of extraterrestrial technology would damage public trust in space science for generations. The community learned painful lessons from premature announcements regarding Martian meteorite biosignatures, claims of bacterial life in Martian rocks that sparked worldwide excitement before careful analysis revealed more mundane explanations. The media amplification effect compounds these concerns. Speculative hypotheses presented as serious possibilities quickly transform into definitive claims through successive reporting cycles. Public understanding suffers when preliminary interpretations receive treatment as established facts, creating unrealistic expectations for revolutionary discoveries. Yet the scientific pushback extends beyond mere institutional conservatism. Technical experts identify specific flaws in exotic interpretation arguments. The orbital mechanics claimed to be improbable actually fall within expected ranges for randomly oriented interstellar trajectories. The chemical anomalies, while interesting, do not exceed the bounds of natural comet diversity projected for objects formed in different stellar environments. The polarimetry signatures, though unusual by solar system standards, could result from dust processing mechanisms active in interstellar space but absent from our local environment. Every supposedly artificial signature admits plausible natural explanations when examined carefully by specialists familiar with the relevant physics. This does not mean that extraordinary hypotheses lack all value. Even incorrect theories can advance knowledge by motivating new observations, encouraging analytical technique development, and forcing precise articulation of what evidence would constitute proof of artificial origin. The alien technology speculation surrounding 3I-ATLAS has generated valuable scientific activity, detailed observational campaigns, improved spectroscopic analysis methods, and enhanced coordination between ground-based and space-based observation programs. These benefits accrue regardless of whether the original hypotheses prove correct. The community's response also highlights healthy self-correction mechanisms within astronomical research. Extraordinary claims receive extraordinary scrutiny through peer review, independent verification attempts, and public debate among experts. This process, though sometimes contentious, ultimately strengthens scientific knowledge by filtering speculation from substantiated discovery. Media coverage has emphasized natural explanations, fitting current data while acknowledging the genuine chemical and physical anomalies that make 3I-ATLAS scientifically interesting. The object represents the most thoroughly observed interstellar visitor in human history, providing unprecedented insights into the diversity of materials formed around other stars. The strongest scientific story emerging from accumulated observations describes a chemically unusual but fundamentally natural comet. Its carbon dioxide-rich composition, early volatile activity, and exotic dust properties reflect formation and evolutionary processes, different from local solar system examples, but not necessarily requiring artificial origin. This interpretation satisfies Occam's razor while accounting for all confirmed observations. It expands our understanding of interstellar object diversity without invoking unverified technological civilizations. It challenges existing theories of comet formation and evolution while remaining grounded in established physical principles. As investigation continues, mainstream science maintains its commitment to evidence-based conclusions while remaining open to genuinely revolutionary discoveries should compelling evidence emerge. The burden of proof for extraordinary claims remains appropriately high, protecting the integrity of astronomical research while allowing space for legitimate scientific surprise. Now we must shift our perspective entirely, examining a radical hypothesis that has begun attracting serious attention from respected planetary formation theorists: the possibility that interstellar objects like 3I-ATLAS serve as ready-made cores for seeding planetary systems throughout the galaxy. Part 6. Suzanne Falsner's idea. In the Max Planck Institute for Radio Astronomy, astrophysicist Susan Falsner has proposed a revolutionary mechanism that could reshape our understanding of planetary formation. Her hypothesis suggests that interstellar objects, wanderers like 3I-ATLAS, might serve as ready-made planetary cores, captured by young stellar systems and rapidly growing into gas giants through accretion processes. This concept elegantly addresses one of planetary formation theory's most persistent puzzles: the timeline problem. Traditional models require millions of years for dust grains to collide, stick together, and gradually build planetesimals large enough to gravitationally attract gas from protoplanetary disks. Yet observations reveal that gas disks around young stars typically disperse within just a few million years. The mathematical challenge appears insurmountable. How can planets grow massive cores quickly enough to capture substantial gaseous envelopes before their stellar host's disk evaporates into space? Conventional core accretion theory struggles to explain the observed abundance of gas giant planets, particularly around more massive stars. Falsner's computer simulations reveal an intriguing pattern. More massive stars appear more effective at capturing interstellar objects gravitationally, and astronomical surveys indeed show higher frequencies of giant planets orbiting larger stellar masses. This correlation provides circumstantial support for the interstellar seeding hypothesis. The capture mechanism operates through gravitational dynamics within dense stellar nurseries. Young stars form in clusters containing hundreds or thousands of siblings, creating gravitationally complex environments where interstellar objects might be exchanged between systems or captured from the general galactic population. Gas drag within protoplanetary disks plays a crucial role in the capture process. When an interstellar object encounters a young stellar system, friction with disk material can reduce its velocity sufficiently for gravitational binding. Once captured, the former wanderer becomes a ready-made planetary core, bypassing the slow initial growth phases that plague traditional formation models. The accretion process then accelerates dramatically. A captured object with radius measured in kilometers rather than meters possesses enormously enhanced gravitational cross-sections for attracting additional material. Growth proceeds through direct collision with disk solids and gravitational focusing of smaller particles, processes that can build substantial masses within timescales compatible with observed disk lifetimes. This rapid core growth enables efficient gas capture during the critical window when protoplanetary disks still retain their gaseous components. The resulting planets might achieve Jovian masses within just a few 100,000 years, rather than the millions required by conventional scenarios. Falsner's theoretical framework makes specific predictions about planetary system architectures. Captured cores would retain chemical signatures, reflecting their formation environments in different stellar systems. The resulting planets might exhibit isotopic ratios, elemental abundances, or volatile inventories distinguishable from purely local formation products. The model also predicts that interstellar object capture rates should correlate with stellar cluster properties. Denser, more massive clusters should facilitate higher capture frequencies, potentially explaining observed correlations between stellar environment and planetary system characteristics. Current observations provide tantalizing hints supporting this framework. The three confirmed interstellar objects discovered so far, 1I/Oumuamua, 2I/Borisov, and 3I-ATLAS, represent only the tip of a much larger population. Detection biases strongly favor larger, more active objects, suggesting that smaller, inactive wanderers vastly outnumber the few we have observed. This hidden population could provide the raw material for Falsner's seeding mechanism. If interstellar space contains millions of dark, inactive objects for every bright comet we detect, the supply of potential planetary cores becomes essentially unlimited across galactic timescales. The chemical diversity exhibited by our small sample of interstellar visitors supports the seeding hypothesis. 1I/Oumuamua showed no detectable volatile activity, suggesting a composition dominated by refractory materials. 2I/Borisov resembled solar system comets closely, indicating formation in environments similar to our own outer system. 3I-ATLAS presents yet another chemical profile, with its carbon dioxide dominance and exotic dust properties. This diversity implies that interstellar objects sample formation conditions across many different stellar environments. Captured cores would import chemical signatures from their birth systems, potentially explaining the observed diversity in exoplanet compositions that the current models struggle to reproduce through purely local processes. The timing of 3I-ATLAS's discovery provides an unprecedented opportunity to test aspects of the seeding hypothesis. Unlike previous interstellar visitors detected after closest approach, this object's early identification enables detailed compositional and structural analysis while it remains relatively nearby. If 3I-ATLAS represents typical seeding material, its properties should reflect characteristics favorable for rapid planetary core growth. The carbon dioxide-rich composition suggests formation in cold, outer system environments, where such volatiles could condense efficiently. The early water activity indicates sufficient porosity and volatile content to drive active outgassing processes. These characteristics might prove advantageous for captured cores. Volatile-rich interiors could facilitate rapid heating and expansion during accretion phases, potentially accelerating the core growth process through enhanced collision cross-sections and improved particle capture efficiency. The object's size range, approximately 0.44 to 5.6 kilometers in diameter, falls within theoretical predictions for effective seed masses. Objects significantly smaller might lack sufficient gravitational influence to rapidly accumulate disk material. Much larger bodies might be too rare to explain observed planetary frequencies. Falsner's hypothesis represents more than abstract theoretical speculation. It makes testable predictions about planetary system properties, interstellar object populations, and correlations between stellar cluster characteristics and planet formation efficiency. These predictions can be evaluated through ongoing and future observational programs. The European Space Agency's Gaia mission has begun identifying potential interstellar objects through precision astrometry of stellar motion patterns. The Vera Rubin Observatory's upcoming legacy survey of Rubin Observatory's Beer, space and time should dramatically expand our census of transient objects, potentially revealing many additional interstellar visitors currently unknown. James Webb Space Telescope. Observations of protoplanetary disks might detect chemical signatures consistent with captured interstellar material. Isotopic ratios, elemental abundances, and volatile inventories informing planetary systems could provide circumstantial evidence for seeding processes. The hypothesis also connects to broader questions about galactic chemical evolution and material exchange between stellar systems. If interstellar seeding operates efficiently, the chemical history of planetary systems becomes entangled across vast spatial and temporal scales. Stellar nurseries would function as mixing chambers, where materials formed around many different stars become redistributed among growing planetary systems. The resulting chemical diversity might exceed what purely local formation processes could achieve, potentially explaining observed exoplanet composition ranges. This galactic perspective transforms planetary formation from an isolated, system-specific process into a collaborative effort involving materials and objects exchanged across interstellar distances. The implications extend beyond technical questions of formation mechanisms to fundamental issues about cosmic connectivity and the shared heritage of planetary systems. 3I-ATLAS, viewed through this lens, represents more than an unusual comet or potential artificial probe. It becomes a messenger carrying chemical memories from distant stellar environments, a sample of the raw materials that might seed planetary formation throughout our galaxy. Whether this particular object ever served such a function remains unknown. It appears destined to escape our solar system rather than joining our planetary family. But its composition and structure provide crucial insights into the kinds of materials available for cosmic seeding processes. Operating throughout galactic history, the seeding hypothesis offers a natural explanation for rapid planetary formation that requires no exotic physics or alien technology. It suggests that the galaxy itself functions as a vast recycling system, redistributing materials and enabling rapid planetary growth through gravitational capture and accretion processes. Yet even this natural seeding mechanism raises profound questions about the origins and distribution of life itself throughout cosmic history. Part 7. Historical Context. To understand why interstellar seeding represents such a revolutionary concept, we must first examine the traditional models that have guided planetary formation theory for decades. The standard paradigm divides giant planet formation into two competing mechanisms: core accretion versus gravitational disk instability, each struggling with fundamental timeline problems that Falsner's seeding hypothesis elegantly circumvents. Core accretion theory requires dust grains within protoplanetary disks to collide and stick together through electrostatic forces, gradually building larger aggregates. These growing particles face the meter-size barrier, a zone where aerodynamic drag becomes so efficient that objects spiral into their host stars before achieving gravitational dominance. The recent discovery of pebble accretion provided one partial solution. Instead of relying solely on random collisions, This mechanism invokes gravitational focusing effects that allow planetesimals to capture streams of smaller particles more efficiently. Yet even pebble accretion requires several million years to build cores massive enough for gas capture. Gravitational disk instability offers an alternative pathway through direct gravitational collapse of dense regions within massive protoplanetary disks. This mechanism can potentially form giant planets within thousands rather than millions of years, but it requires specific disk conditions, high mass, low temperature, and gravitational instabilities that may not exist around most young stars. Both traditional mechanisms face the harsh reality of observational constraints. Protoplanetary disk masses measured around young stars often appear insufficient for either core accretion or disk instability to operate efficiently. Gas disk lifetimes, constrained through observations of stellar nurseries, typically range from 1 to 10 million years, barely sufficient for conventional planet formation timescales. The timeline pressure becomes especially acute for massive stars, which tend to disperse their protoplanetary disks more rapidly through intense stellar winds and radiation pressure. Yet surveys reveal that more massive stars actually host giant planets more frequently than lower mass counterparts, exactly the opposite of what conventional formation theory predicts. Could external seeding have operated within our own solar system during its formation 4.6 billion years ago? The possibility remains entirely speculative, but circumstantial evidence suggests that interstellar object influx rates might have been substantially higher in the early galaxy. Our solar system formed within a stellar nursery, containing hundreds or thousands of sibling stars born from the same giant molecular cloud. This dense environment would have facilitated gravitational interactions, stellar encounters, and potential interstellar object exchanges between forming planetary systems. Additionally, 3I-ATLAS may originate from the galaxy's thick disk population, stars formed during earlier epochs when the Milky Way possessed different chemical composition and stellar density profiles. If confirmed, this ancient heritage suggests that interstellar wanderers might carry chemical memories spanning billions of years of galactic evolution. The thick disk connection raises intriguing possibilities about cosmic recycling processes operating over geological timescales. Materials, ejected from planetary systems billions of years ago, might eventually find their way into newly forming systems, creating complex webs of chemical inheritance across galactic space and time. This perspective transforms our understanding of planetary system formation from isolated, independent processes into interconnected phenomena, sharing materials and evolutionary histories across vast cosmic scales. Jupiter and Saturn might incorporate trace amounts of materials originally formed around stars that died before our Sun was even born. The comparison with previous interstellar visitors illuminates how composition and activity patterns influence interpretation of these cosmic wanderers. 2I/Borisov closely resembled typical solar system comets in its chemical signature, volatile activity, and dust production, suggesting formation in an environment similar to our own outer system. 1I/Oumuamua presented the opposite extreme: no detectable outgassing, unusual acceleration patterns, and geometric constraints, suggesting an elongated or flattened shape unlike typical comets or asteroids. This combination of properties sparked the initial speculation about artificial origins that continues echoing in discussions of 3I-ATLAS. 3I-ATLAS occupies middle ground between these extremes. It exhibits clear cometary activity through gas and dust production, but with chemical signatures distinctly different from both solar system comets and 2I/Borisov. This intermediate position makes it particularly valuable for understanding the full spectrum of interstellar object diversity. The chemical diversity among our small sample of interstellar visitors hints at the variety of formation environments, sampling different stellar system architectures, evolutionary histories, and galactic chemical evolution epochs. Each object carries unique fingerprints of its birth environment, potentially enabling retrospective studies of conditions around other stars. Frequency estimates for interstellar object populations remain highly uncertain, but recent theoretical work suggests that our solar system might encounter several objects per year in the size range of 3I-ATLAS. Most pass undetected due to their small size, inactive nature, or unfavorable observation geometries. The Vera Rubin Observatory's legacy survey of space and time beginning operations in the mid-2020s, should revolutionize our census of transient objects, including interstellar visitors. This facility will monitor the entire visible sky every few nights, detecting moving objects through comparison of successive images. Statistical projections suggest that Rubin might identify hundreds of interstellar objects annually, once reaching full operational capacity. This dramatic increase in sample size will enable robust tests of seeding hypothesis predictions about population characteristics, size distributions, and chemical diversity patterns. Enhanced detection capabilities will also permit more accurate assessment of capture probabilities within young stellar systems. If interstellar objects prove far more abundant than currently estimated, the raw material supply for seeding mechanisms becomes correspondingly more plentiful. The seeding framework makes specific predictions about correlations between stellar cluster properties and resulting planetary system architectures. Dense, massive clusters should facilitate higher capture rates, potentially explaining observed relationships between stellar environment and planet occurrence frequencies. These predictions become testable through combination of Gaia astrometry data, which traces stellar birth cluster associations, with exoplanet surveys that characterize planetary system properties around stars with known formation environments. Statistical analyses might reveal signatures of seeding processes operating during the early phases of planetary system formation. The historical context also encompasses broader questions about galactic chemical evolution and material redistribution processes. If seeding operates efficiently throughout cosmic history, the chemical signatures of planetary systems become entangled across vast spatial and temporal scales. This galactic mixing perspective suggests that the chemical diversity observed in exoplanet atmospheres and bulk compositions might exceed what purely local formation processes could achieve. The range of available materials expands dramatically when formation regions can import components originally condensed around stars with different masses, metallicities, and evolutionary histories. 3I-ATLAS, viewed within this historical framework, represents a unique opportunity to study materials that might once have participated in seeding processes, even though this particular object appears destined for interstellar escape rather than capture by our solar system. The combination of early discovery, detailed observation campaigns, and advanced analytical techniques provides unprecedented insights into the composition and structure of potential seeding materials. Whether or not 3I-ATLAS ever functioned as a planetary core, it offers crucial data for understanding the kinds of objects available for cosmic seeding throughout galactic history. The seeding hypothesis transforms interstellar objects from mere curiosities into potential architects of planetary diversity, suggesting that worlds throughout our galaxy might share more complex heritage relationships than previously imagined. Part 8. 3I-ATLAS as a test case. The carbon dioxide dominance observed in 3I-ATLAS provides our first crucial test of the seeding hypothesis. This chemical signature could trace formation in environments far colder and more carbon dioxide rich than typical solar system comet-forming regions. Such extreme conditions might exist in the outer reaches of massive protoplanetary disks or around low-mass stars with extended snowline boundaries. For seeding purposes, this composition profile could prove advantageous rather than anomalous. Carbon dioxide remains stable at higher temperatures than water ice, potentially enabling volatile-driven outgassing across wider ranges of stellar distances. A seed with high carbon dioxide content might remain active during capture phases, when water-dominated objects would remain dormant. The early hydroxyl activity detected at 3.5 astronomical units demonstrates that 3I-ATLAS contains substantial water ice, despite its carbon dioxide-rich coma. This combination suggests a layered or mixed volatile structure, capable of producing both early water signatures and sustained carbon dioxide emission, as solar heating penetrates deeper into the nucleus. Such complex volatile architecture would benefit captured seeds by providing multiple mechanisms for expansion and particle capture enhancement during accretion phases. Early water outgassing could create extended atmospheres that increase collision cross-sections for intercepting disk materials. Later, carbon dioxide emission might sustain this process across longer timescales and wider orbital distances. The polarimetry measurements revealing unusual dust properties strengthen the case for exotic formation environments. The extended negative polarization branch and distinctive scattering behavior suggest grain populations with porosity levels, size distributions, or compositional characteristics, unlike solar system comets. These dust properties might reflect processing in interstellar environments over extended timescales. Cosmic ray bombardment, stellar wind interactions, and thermal cycling during million-year journeys between stars could modify grain structures in ways impossible within individual stellar systems. For seeding applications, unusual dust properties could enhance accretion efficiency through several mechanisms. High porosity materials exhibit larger geometric cross-sections relative to their masses, improving collision probabilities with disk particles. Distinctive optical properties might indicate chemical compositions particularly effective for catalyzing subsequent grain growth processes. The size constraints derived from Hubble Space Telescope observations place 3I-ATLAS diameter between approximately 0.44 and 5.6 kilometers. This range occupies a potentially optimal zone for seeding effectiveness, large enough to provide substantial gravitational influence, yet small enough to be captured efficiently by gas drag within protoplanetary disks. Objects significantly smaller than this range might lack sufficient mass for rapid accretion of disk materials. Much larger bodies could prove too massive for effective capture, requiring prohibitively specific encounter geometries to achieve gravitational binding within young stellar systems. The intermediate size scale also implies that 3I-ATLAS represents accessible raw material for seeding processes rather than rare massive planetesimals. Theoretical models suggest that objects in this size range might be produced relatively abundantly through collisional grinding of larger bodies or direct condensation in outer disk regions. Kinematic analysis indicates possible thick disk origins for 3I-ATLAS, suggesting formation during earlier epochs of galactic evolution, when stellar densities, metallicities, and chemical processing mechanisms differed substantially from present conditions. This ancient heritage could provide insights into seeding materials available during the universe's earlier phases. If confirmed, the thick disk connection implies that 3I-ATLAS carries chemical memories spanning potentially billions of years. The isotopic ratios, elemental abundances, and molecular inventory preserved within its nucleus might sample conditions from stellar formation epochs preceding our solar system's birth. This temporal perspective transforms 3I-ATLAS from a contemporary curiosity into an archaeological sample of ancient galactic chemistry. The materials it contains might include components originally formed around stars that completed their entire life cycles before our Sun began nuclear fusion. The cyanogen detection strengthens the chemical inventory available for seeding processes by confirming complex carbon-nitrogen chemistry within the nucleus. CN emission typically correlates with organic compound sublimation, suggesting that 3I-ATLAS carries prebiotic molecular building blocks alongside its unusual volatile mixture. For seeding scenarios involving life's chemical precursors, this organic content could prove crucial. Captured objects carrying diverse organic inventories might deliver complex chemistry directly into forming planetary systems, potentially accelerating prebiotic evolution processes within newly formed worlds. The nickel emission lines, while not necessarily indicating industrial processing, do demonstrate that 3I-ATLAS contains refractory elements alongside its volatile components. This mixed composition provides both the volatile drivers necessary for active outgassing and the solid materials required for substantial planetary core construction. The combination of volatiles and refractories within a single object offers advantages for seeding mechanisms. The volatile components enable rapid expansion and enhanced particle capture during early accretion phases. The refractory materials provide the solid foundation necessary for sustained gravitational growth toward planetary masses. Spectroscopic analysis reveals additional chemical complexity through detection of multiple emission lines spanning diverse molecular and atomic species. This chemical diversity suggests formation in environments capable of preserving wide ranges of materials rather than the highly processed conditions that might characterize purely local formation scenarios. The preservation of chemical diversity within 3I-ATLAS implies minimal thermal processing during its interstellar journey. This conclusion supports the feasibility of transporting complex chemistry across interstellar distances without complete molecular destruction through cosmic ray bombardment or stellar encounter heating. Current observations establish that 3I-ATLAS exhibits several characteristics consistent with effective seeding material: appropriate size range, complex chemical inventory, mixed volatile and refractory composition, and exotic formation environment signatures. However, direct testing of seeding effectiveness remains impossible, since this particular object appears destined for interstellar escape. The capture dynamics that would enable seeding require specific encounter geometries with young stellar systems possessing massive protoplanetary disks. 3I-ATLAS currently follows a hyperbolic trajectory that will carry it away from our solar system after completing its current passage. This escape trajectory actually provides valuable scientific opportunities by enabling detailed study of seeding material composition and structure without the complications introduced by permanent gravitational capture. We can analyze 3I-ATLAS as a representative sample while it remains accessible to our observational capabilities. The chemical fingerprinting currently underway through multiple telescope observations will establish benchmarks for recognizing similar materials in other contexts. Future discoveries of captured interstellar objects within exoplanetary systems might be identified through comparison with the detailed compositional profile now being assembled for 3I-ATLAS. The isotopic ratios, elemental abundances, and molecular inventories measured during the current observational campaign will become reference standards for distinguishing seeding materials from locally formed planetary system components. This reference library approach could enable retrospective identification of seeding signatures within mature planetary systems. 3I-ATLAS thus serves dual scientific purposes: testing the plausibility of seeding material characteristics and establishing observational benchmarks for recognizing seeding processes in other stellar systems. Whether or not this particular object ever participated in planetary formation, it provides crucial insights into the raw materials available for cosmic seeding throughout galactic history. The verdict for 3I-ATLAS as seeding material remains preliminary but encouraging. It exhibits multiple characteristics consistent with effective seed composition and structure, while providing unprecedented opportunities for detailed analysis of interstellar object properties. Yet, if seeds routinely cross between stellar systems carrying complex chemistry and diverse materials, could they also transport the most complex chemistry of all, the molecular foundations of life itself? Part 9. Broader implications. The concept of interstellar objects serving as cosmic couriers fundamentally transforms our understanding of material exchange between stellar systems. Rather than isolated islands of chemistry, planetary systems become nodes in a vast galactic network where ices, organics, and minerals flow along gravitational currents spanning light years and eons. This cosmic cross-pollination operates on timescales that dwarf human experience but prove brief in galactic terms. A single interstellar object might carry materials between dozens of stellar encounters during million-year journeys through the galaxy's gravitational landscape. Each encounter offers potential for capture, delivery, or exchange of chemical cargo accumulated across previous stellar system visits. The statistical implications prove staggering when projected across galactic populations. Our Milky Way contains approximately 400 billion stars, most of which likely hosted protoplanetary disks during their youth. If even a tiny fraction of these systems exchanged materials through interstellar object transport, the cumulative effect would create chemical mixing on unprecedented scales. This perspective links directly to panspermia hypotheses, the possibility that life's ingredients or life itself might travel between worlds on natural spacecraft. The traditional version envisions rocks blasted from planetary surfaces, carrying dormant microbes to new homes among the stars. Interstellar objects offer a more elegant mechanism: purpose-built vessels optimized for interstellar survival and chemical preservation. Unlike impact ejecta, which typically originate from planetary surface materials, interstellar objects likely sample deeper, more primitive compositions that experienced minimal thermal processing. These pristine chemical inventories might preserve complex organic molecules, isotopic signatures, and even biological materials across interstellar distances. The survivability question remains central to evaluating panspermia scenarios. Cosmic ray bombardment presents the primary threat to complex chemistry during extended interstellar journeys. However, calculations suggest that several meters of ice and dust shielding, easily achievable within objects like 3I-ATLAS, could reduce radiation exposure to biologically tolerable levels. Recent theoretical work has refined these survival estimates by considering the protective effects of magnetic fields generated within conducting materials, chemical repair mechanisms that might operate even at low temperatures, and statistical distributions of cosmic ray exposure that create radiation shadows within object interiors. The results suggest cautious optimism for preserving complex organic chemistry, though the survival of actual living organisms remains speculative. The more conservative scenario involves delivery of prebiotic building blocks, rather than fully functional biological systems, still revolutionary for understanding life's cosmic distribution. Statistical projections based on improved interstellar object population estimates suggest encounters with our solar system occur far more frequently than the 3 confirmed detections might imply. Most visitors likely pass unnoticed due to their small size, inactive nature, or unfavorable observation geometries relative to Earth-based detection capabilities. The Vera Rubin Observatory's upcoming census should dramatically expand our statistical sample, potentially revealing hundreds of interstellar visitors annually. This enhanced detection rate will enable robust testing of seeding hypothesis predictions, while providing multiple opportunities to study diverse chemical compositions and structural characteristics. If Rubin's projections prove accurate, the raw material supply for seeding mechanisms becomes essentially unlimited across cosmic timescales. Young stellar systems would encounter potential seed materials routinely rather than rarely, making capture events statistically inevitable rather than extraordinary. The chemical diversity already evident among our tiny sample of interstellar objects, 1I/Oumuamua, 2I/Borisov, and 3I-ATLAS, hints at the variety of materials sampling different stellar formation environments, evolutionary histories, and galactic chemical evolution epochs. This diversity suggests that seeding processes might import chemical signatures spanning the full range of galactic metallicity evolution, stellar mass distributions, and planetary system architecture types. The resulting chemical mixing could produce planetary compositions that exceed what purely local formation processes might achieve. Oumuamua's apparent lack of volatile activity, combined with unusual geometric constraints, suggests formation in environments dominated by refractory materials. Borisov's close resemblance to solar system comets indicates formation in conditions similar to our own outer planetary region. 3I-ATLAS presents yet another chemical profile entirely, with carbon dioxide dominance and exotic dust properties. This spectrum of compositions implies that different stellar systems contribute distinct chemical signatures to the interstellar object population. Massive stars might eject carbon-rich materials from their extensive protoplanetary disks. Low-mass stars could contribute water-dominated compositions formed in their cooler, extended snowline regions. The temporal dimension adds further complexity to this chemical mixing process. Objects like 3I-ATLAS, potentially originating from thick disk populations, might carry chemical memories from galactic epochs billions of years in the past. Their compositions could sample stellar formation conditions that no longer exist in the present-day galaxy. This archaeological perspective transforms interstellar objects into time capsules preserving ancient galactic chemistry. Their isotopic ratios, elemental abundances, and molecular inventories might provide unique windows into cosmic chemical evolution, otherwise inaccessible through conventional astronomical observations. The life-seeding angle, while speculative, deserves serious consideration given the stakes involved. If interstellar objects routinely transport prebiotic chemistry between stellar systems, the emergence of life might prove far more probable than calculations based on purely local chemical evolution would suggest. This distributed approach to prebiotic chemistry could operate like a vast mycelial network spanning galactic distances. Individual stellar systems become nodes, where complex molecules accumulate, evolve, and propagate to neighboring systems through interstellar object transport. The collective chemical evolution might far exceed what any single system could achieve independently. However, the survival challenges remain formidable across geological timescales typical of interstellar journeys. Radiation damage, thermal cycling, and chemical decomposition processes could destroy complex organic molecules long before they reach suitable delivery targets. The more realistic scenario involves delivery of simpler organic building blocks rather than complex biomolecules or living organisms. Even this conservative version would prove revolutionary by demonstrating that life's chemical foundations might be distributed throughout the galaxy, rather than emerging independently within each suitable environment. Recent advances in extremophile biology have revealed organisms capable of surviving conditions once thought impossibly harsh for life. Some bacteria tolerate radiation doses thousands of times higher than previous estimates of biological limits. Others remain viable for decades in complete vacuum or at temperatures near absolute zero. These discoveries expand the parameter space for possible biological survival during interstellar transport, though the combination of multiple extreme conditions during million-year journeys still presents extraordinary challenges for even the hardiest known organisms. The ethical and philosophical implications of confirmed cosmic seeding, whether natural or artificial, extend far beyond technical questions of planetary formation mechanisms. If worlds throughout the galaxy share common chemical heritage through material exchange processes, the boundaries between local and foreign chemistry become meaningless. This galactic perspective suggests that Earth's biosphere might incorporate materials originally formed around countless other stars across billions of years of cosmic evolution. Our planet becomes not an isolated world, but a collaborative creation involving chemical contributions from the entire galactic community. 3I-ATLAS, viewed through this lens, represents far more than an unusual comet or potential artificial probe. It becomes a messenger, carrying memories from distant stellar environments, a sample of the materials that might have participated in seeding processes throughout cosmic history. Whether this particular object ever delivered its cargo to a receptive young planetary system remains unknown, but its composition and structure provide unprecedented insights into the kinds of materials available for cosmic cross-pollination throughout our galaxy's evolutionary history. Could some seeds carry more than chemistry? Could they transport actual biology while being designed to create the conditions necessary for planetary formation itself? Part 10. The Alive Planet Seed Concept. The synthesis of two radical concepts, interstellar objects as planetary seeds, and the possibility of life within these cosmic wanderers, creates perhaps the most speculative yet fascinating scenario in our investigation. What if 3I-ATLAS represents not merely a chemical delivery system, but a living spacecraft designed to fundamentally alter the planetary formation process itself? Scenario A envisions dormant microorganisms embedded within a robust, carbon dioxide-rich matrix that provides both protection and sustenance during million-year interstellar journeys. These microscopic passengers would remain in cryptobiotic suspension, their metabolic processes slowed to imperceptible rates, while cosmic radiation slowly degrades their cellular machinery. The carbon dioxide dominance observed in 3I-ATLAS might serve multiple biological functions. This molecule provides an excellent radiation shielding material while remaining chemically stable across extreme temperature ranges. Additionally, carbon dioxide could serve as a carbon source for autotrophic organisms capable of fixing atmospheric carbon into organic compounds when conditions permit. During warm passages near stellar encounters, interior heating might create transient zones of liquid water within the porous matrix. These brief oases could awaken dormant biology, enabling rapid reproduction, metabolic activity, and dispersal of biological materials into the surrounding environment through outgassing processes. The speculative biology would need to exhibit extraordinary resilience characteristics, far exceeding any known terrestrial organisms. Resistance to cosmic radiation doses accumulated over geological timescales, survival in vacuum conditions, tolerance for extreme temperature cycling, and ability to remain viable without metabolic activity for millions of years. Recent discoveries of extremophile organisms on Earth provide tantalizing hints that such capabilities might exist within the realm of biological possibility. Deinococcus radiodurans survives radiation exposures thousands of times higher than lethal doses for most life forms. Tardigrades endure vacuum conditions, extreme temperatures, and decades of complete desiccation while retaining viability upon rehydration. Scenario B ventures into even more speculative territory. Engineered probes that deliberately manipulate protoplanetary disk material through controlled outgassing, designed to optimize planetary formation conditions. Rather than passive seeds awaiting capture, these objects might actively participate in terraforming entire stellar systems. The sunward dust plume observed in 3I-ATLAS could theoretically represent deliberate material injection into our solar system's space environment. If the object contains programmable matter or self-modifying systems, the outgassing patterns might follow complex algorithms designed to achieve specific chemical or physical objectives. This scenario requires technology capable of operating autonomously across million-year timescales while adapting to unpredictable encounter conditions with diverse stellar systems. The engineering challenges appear nearly insurmountable using any conceivable technology, yet the concept remains theoretically possible for sufficiently advanced civilizations. The observable signatures that might distinguish such exotic scenarios from natural phenomena include repeatable jet patterns that correlate with programmed objectives rather than solar heating cycles. Course corrections, inconsistent with natural sublimation physics, might indicate active attitude control systems. Narrowband emissions at specific frequencies could suggest communication systems or technological power sources. Current observations reveal none of these decisive technological signatures. 3I-ATLAS behaves consistently with natural comet physics across all measured parameters, exhibiting outgassing patterns that correlate predictably with solar heating and rotational dynamics. The absence of obvious artificial signatures does not completely eliminate exotic hypotheses, but it requires increasingly sophisticated explanations for why advanced technology would remain perfectly camouflaged while accomplishing complex objectives through apparently natural processes. The why now question adds another layer of complexity to artificial scenarios. If 3I-ATLAS represents deliberate reconnaissance or terraforming technology, why would it reveal itself during this particular epoch of human technological development? Abraham Loeb's interpretation suggests that the perihelion passage behind the Sun might reduce observational opportunities from Earth-based telescopes, providing operational security for sensitive activities. However, this explanation assumes that hypothetical alien civilizations possess detailed knowledge of human observational capabilities, while lacking awareness of our extensive space-based astronomy infrastructure. The philosophical dimensions of confirmed alive planet seed scenarios would fundamentally transform human understanding of our cosmic context and responsibilities. If the galaxy operates as a vast gardening system, where intelligence seeds planetary formation processes, our species might be products of deliberate cultivation, rather than random evolutionary processes. This perspective raises profound questions about autonomy, purpose, and obligation. Would humanity bear responsibilities to continue hypothetical gardening activities? Should we attempt contact with the gardeners? How would confirmed cultivation affect human cultural and religious frameworks built around assumptions of cosmic isolation? The ethical implications become even more complex if seeding processes operate through biological rather than technological mechanisms. Natural panspermia would suggest that life throughout the galaxy shares common ancestry, making all biological systems extended family members separated by space and time, rather than fundamental evolutionary barriers. Artificial seeding scenarios introduce questions about the intentions and capabilities of hypothetical cosmic gardeners. Benevolent cultivation aimed at maximizing life's distribution throughout the galaxy would imply profoundly different relationships with potential alien civilizations compared to scenarios involving surveillance, manipulation, or exploitation. The current observational evidence provides no support for extraordinary biological or technological interpretations of 3I-ATLAS. The object exhibits chemical and physical anomalies that intrigue scientists, while remaining fully consistent with natural formation and evolutionary processes. However, the speculative scenarios serve valuable functions by expanding conceptual horizons and motivating development of more sophisticated detection techniques for genuine biological or technological signatures, should they exist in other contexts. The burden of extraordinary proof remains appropriately high for claims involving biology or technology within interstellar objects. The scientific method demands reproducible evidence rather than speculative interpretation of ambiguous observations. Yet the philosophical value of exploring these concepts extends beyond their immediate scientific plausibility. They force examination of assumptions about life's cosmic distribution, intelligence's role in planetary formation, and humanity's position within potentially vast networks of biological or technological activity. The alive planet seed concept also highlights the interconnected nature of cosmic processes that might operate across scales, spanning individual molecules to entire galactic populations. If life participates in planetary formation, either naturally or artificially, the boundaries between geology, biology, and technology become increasingly meaningless. 3I-ATLAS, whether it ultimately proves natural, biological, or technological, has already succeeded in expanding human perspective about the possibilities hidden within cosmic phenomena that initially appear mundane. The investigation process itself demonstrates science's capacity for serious consideration of radical hypotheses, while maintaining rigorous standards for evidence evaluation. The speculative nature of alive planet seed scenarios does not diminish their value for motivating improved observational techniques, theoretical framework development, and philosophical examination of humanity's cosmic context. Even incorrect hypotheses can advance knowledge by clarifying what evidence would constitute proof of extraordinary claims. As 3I-ATLAS continues its journey toward perihelion and beyond, the mounting observational evidence will ultimately determine which interpretation, natural, biological, or technological, best explains this enigmatic visitor from the space between stars. The next 6 to 12 months may provide the definitive data needed to resolve these fundamental questions about the nature of our interstellar guest and its implications for understanding planetary formation, life's distribution, and intelligence's role in cosmic evolution. Part 11. Upcoming observations. October 3rd, 2025 marks our first crucial observational milestone as 3I-ATLAS approaches within approximately 30 million kilometers of Mars. The European Space Agency has confirmed that Mars Express and ExoMars Trace Gas Orbiter will attempt coordinated observations using their high-resolution stereo camera, color, and stereo surface imaging system, and additional specialized payloads. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment has been mentioned in several outlets as potentially joining this observational campaign, though scheduling conflicts with ongoing surface operations may limit its availability. Each instrument offers unique capabilities for analyzing coma structure, jet patterns, and color variations that could distinguish natural outgassing from artificial emissions. The proximity to Mars provides unprecedented opportunities for high-resolution imaging at wavelengths impossible to achieve from Earth-based telescopes. The reduced distance eliminates atmospheric distortion, while enabling temporal monitoring of outgassing variations across multiple rotational periods. Spectroscopic capabilities aboard the Mars orbiters could detect emission lines invisible from Earth due to atmospheric absorption or insufficient spectral resolution. The detection of additional molecular species, unusual isotopic ratios, or artificial emission signatures would dramatically alter interpretations of 3I-ATLAS's nature and origin. October 29th brings perihelion passage at approximately 1.36 astronomical units from the Sun, unfortunately positioned behind our star from Earth's perspective. This cosmic alignment prevents direct observation using most ground-based and Earth-orbiting telescopes during the critical phase when solar heating reaches maximum intensity. However, several space-based assets positioned at the Sun-Earth Lagrange point 1, or within the inner solar system, might maintain sightlines to 3I-ATLAS during perihelion. The Solar and Heliospheric Observatory, Parker Solar Probe, and the upcoming polarimeter to unify the corona and heliosphere mission could potentially observe the object during its closest solar approach. These observations would capture 3I-ATLAS at maximum activity levels, when volatile sublimation rates peak, and any artificial systems might reveal their technological signatures most clearly. The intense solar radiation environment during perihelion could trigger responses from hypothetical, biological or technological components that remain dormant at greater distances. Mars-based observations might provide oblique viewing angles to the perihelion region, though the geometry remains challenging for detailed analysis. The combination of multiple viewpoints from different spacecraft could enable three-dimensional reconstruction of coma structure and outgassing patterns impossible to achieve from single observation platforms. Early December 2025 promises the return of Earth-based observation opportunities, as 3I-ATLAS emerges from behind the Sun at distances permitting renewed telescope access. The James Webb Space Telescope stands ready to resume detailed spectroscopic analysis with dramatically improved sensitivity compared to pre-perihelion observations. Ground-based observatories worldwide will coordinate intensive monitoring campaigns to document any changes in chemical composition, outgassing patterns, or physical structure resulting from the intense solar heating experienced during perihelion passage. The Vera Rubin Observatory's commissioning activities might enable rapid cadence observations, tracking brightness variations and morphological evolution. The post-perihelion phase offers crucial tests for distinguishing natural evolution from artificial behavior. Natural comets typically exhibit predictable changes in volatile production rates, dust emission patterns, and coma chemistry following close solar encounters. Any deviations from established sublimation physics could indicate artificial control systems or biological responses to environmental changes. December 19, 2025, represents the optimal Earth observation window when 3I-ATLAS reaches approximately 1.8 astronomical units distance, close enough for detailed study, yet far enough to avoid solar interference. This geometry enables comprehensive analysis using humanity's most powerful astronomical instruments, without the complications of solar proximity. The Hubble Space Telescope and James Webb Space Telescope will coordinate unprecedented spectroscopic surveys covering ultraviolet through infrared wavelengths. These observations could detect isotopic signatures, revealing formation environments, organic compounds indicating prebiotic chemistry, or artificial emission lines suggesting technological origins. Ground-based facilities, including the Very Large Telescope, Keck Observatory, and Atacama Large Millimeter Array, will contribute complementary observations spanning radio through optical wavelengths. The coordinated campaign represents the most comprehensive study ever attempted of an interstellar visitor during optimal viewing conditions. March 16, 2026, delivers the mission's grand finale, as 3I-ATLAS approaches within 0.36 astronomical units of Jupiter. This close encounter offers potential leverage of Jupiter system assets, though operational realities impose significant constraints on available observation opportunities. Proposals have been published suggesting that NASA's Juno orbiter could modify its trajectory to observe 3I-ATLAS during the Jovian encounter. However, these proposals remain purely theoretical exercises rather than approved mission extensions. Fuel limitations, operational risks, and primary science priorities make such trajectory modifications extremely unlikely, without compelling evidence of extraordinary phenomena. The Psyche spacecraft, currently en route to its asteroid target, might provide opportunistic remote sensing capabilities if geometric alignments prove favorable. Similarly, the European Space Agency's Jupiter Icy Moons Explorer mission could potentially observe 3I-ATLAS from distance, though such observations would represent secondary objectives rather than primary mission activities. The Jupiter encounter geometry offers unique opportunities for gravitational physics experiments. Precise tracking of 3I-ATLAS's trajectory during the close approach could detect tiny deviations from pure gravitational predictions that might indicate artificial propulsion systems or unusual mass distributions within the nucleus. The intense radiation environment near Jupiter might trigger responses from hypothetical, biological, or technological components that remain inactive under normal interstellar conditions. Any artificial systems designed to operate in high radiation environments might reveal themselves most clearly during this phase of the mission. NASA's comprehensive asset list for the 3I-ATLAS observation campaign reads like an inventory of humanity's greatest space-based instruments: Hubble Space Telescope, James Webb Space Telescope, Transiting Exoplanet Survey Satellite, Neil Gehrels Swift Observatory, Sphere-X, Mars rovers and orbiters, Parker Solar Probe, Punch, Solar and Heliospheric Observatory, Europa Clipper, Jupiter Icy, Moons Explorer, Lucy, and Psyche represent unprecedented coordinated efforts spanning multiple space agencies and scientific disciplines. This massive coordination effort reflects the scientific community's recognition that 3I-ATLAS represents a unique opportunity for advancing our understanding of interstellar objects, planetary formation processes, and potentially revolutionary discoveries about life or intelligence in the cosmos. The temporal sequence of observations enables multiple independent tests of hypotheses about 3I-ATLAS's nature and origin. Early Mars observations establish baseline activity patterns. Perihelion passage tests responses to extreme heating. Post-perihelion Earth observations document evolutionary changes. Jupiter encounter provides final gravitational and radiation environment tests. Each observational phase carries specific capabilities and limitations that complement other campaign elements. Mars orbiters offer high spatial resolution but limited spectroscopic capabilities. Earth-based telescopes provide comprehensive spectral coverage but suffer atmospheric interference. Space-based assets eliminate atmospheric effects but carry instrument-specific wavelength restrictions. The coordination challenges alone represent significant achievements in international scientific cooperation. Scheduling observations across multiple space agencies, prioritizing limited observation time on oversubscribed facilities, and coordinating data analysis efforts require unprecedented levels of collaboration. The observation campaign timeline stretches across 8 months of intensive monitoring using humanity's most sophisticated astronomical instruments. Never before have we possessed such comprehensive surveillance capabilities for studying an interstellar visitor throughout multiple phases of its solar system passage. The data volumes expected from this campaign will require new approaches to storage, analysis, and interpretation. Machine learning algorithms, automated spectral analysis techniques, and collaborative data sharing protocols are being developed specifically for handling the unprecedented information stream from 3I-ATLAS observations. Yet the ultimate value of this observational bonanza depends entirely on what the data reveals about the fundamental nature of our enigmatic visitor. The most sophisticated instruments in human history stand ready to detect signatures that could revolutionize our understanding of planetary formation, life's cosmic distribution, or intelligence's role in galactic evolution. The next phase of our investigation must examine exactly what these remarkable instruments might be capable of revealing, and what evidence would definitively separate natural phenomena from the extraordinary alternatives that continue to capture scientific and public imagination alike. Part 12. What the data could reveal. Isotopic spectroscopy represents perhaps our most powerful tool for determining where 3I-ATLAS originally formed within the galaxy's vast chemical landscape. The ratios of deuterium to hydrogen in water vapor, carbon-13 to carbon-12 in carbon dioxide, nitrogen-15 to nitrogen-14 in cyanogen, and oxygen-18 to oxygen-16 in various compounds serve as chemical fingerprints that preserve formation, environment conditions across geological timescales. Each stellar system exhibits distinct isotopic signatures, reflecting the specific nuclear processes, chemical evolution history, and environmental conditions present during planetary formation epochs. Extreme isotopic ratios compared to solar system norms would indicate formation around stars with different masses, metallicities, or evolutionary stages, providing crucial constraints on 3I-ATLAS's birthplace and journey history. The deuterium to hydrogen ratio proves particularly diagnostic because deuterium abundance varies dramatically across different cosmic environments. Formation in cold outer disk regions produces higher deuterium enrichment compared to warmer inner system conditions. Interstellar processing can also modify these ratios through selective photodissociation and chemical fractionation processes. Gas chemistry evolution tracking offers another powerful diagnostic for distinguishing natural sublimation physics from artificial control systems. Natural comets exhibit predictable changes in carbon dioxide to water ratios, carbon monoxide production rates, and volatile species. Emergence patterns as solar heating penetrates progressively deeper into nucleus layers. Artificial systems might exhibit chemistry evolution patterns that deviate systematically from temperature-driven sublimation models. Controlled volatile release, timed emission sequences, or chemical compositions that remain constant despite changing solar heating would indicate active management rather than passive thermal processing. The James Webb Space Telescope's unprecedented spectroscopic sensitivity enables detection of trace molecular species invisible to previous generations of instruments. Complex organic compounds, unusual isotopic variants, or artificial emission signatures might emerge from the enhanced data quality achieved through space-based infrared spectroscopy. Non-gravitational acceleration measurements provide the most direct test for artificial propulsion systems operating below current detection thresholds. High-precision astrometry, combined with occultation timing observations, could potentially detect thrust-like signals down to approximately 10 to the negative 13th astronomical units per day squared. This sensitivity level approaches the theoretical limits imposed by solar radiation pressure and natural outgassing forces, enabling definitive tests for artificial acceleration signatures that exceed natural comet behavior. Persistent, directional accelerations, inconsistent with sublimation-driven forces, would provide compelling evidence for technological propulsion systems. The absence of anomalous accelerations in current datasets reflects either the natural origin of 3I-ATLAS or the extremely subtle nature of any hypothetical artificial propulsion systems. Higher precision measurements during upcoming observation phases may refine these constraints significantly. Coma morphology analysis, through high-cadence imaging from Mars orbiters, could reveal periodic jet patterns, geometric symmetries, or sun-independent structures that indicate active control systems rather than passive thermal response. Natural comets typically exhibit jet activity correlated with rotation periods and solar heating patterns that follow predictable thermal physics. Artificial jets might operate on timing sequences disconnected from natural thermal cycles, maintain pointing directions inconsistent with temperature gradients, or exhibit brightness variations, following programmed rather than physical patterns. The high spatial and temporal resolution available from Mars-based observations enables detailed analysis of jet behavior impossible from Earth-based telescopes. European Space Agency mission planners have confirmed that Mars Express and ExoMars Trace Gas Orbiter possess imaging capabilities sufficient for detecting jet structures down to kilometer scales during the October 3rd close. Approach. This resolution enables morphological analysis comparable to detailed solar system comet studies. Dust polarimetry measurements continue mapping the negative polarization branch and phase angle behavior that distinguishes 3I-ATLAS from typical solar system comets. These optical properties reflect fundamental grain characteristics including size distributions, porosity levels, compositional variations, and internal structures that preserve formation environment signatures. Natural explanations for unusual polarimetry include exotic grain processing during extended interstellar journeys, formation in environments with different dust condensation physics, or compositional differences reflecting non-solar stellar chemistry. Artificial explanations might involve engineered particles designed for specific optical or physical properties. The distinction between exotic natural processes and artificial engineering remains challenging using polarimetry alone. However, combined with other diagnostic techniques, unusual optical behavior contributes to the overall pattern recognition needed for definitive classification. Metals and organics detection represents another crucial diagnostic frontier, where improving instrumental capabilities may reveal decisive evidence for natural versus artificial origins. The current nickel detection without corresponding ion signatures intrigues researchers while remaining consistent with natural excitation and abundance effects. Future observations will search for additional metallic species, complex organic molecules, and isotopic variants that could indicate either exotic natural chemistry or artificial processing. The detection of clearly artificial molecular signatures compounds impossible to produce through known cosmic chemistry, would provide definitive evidence for technological origins. Complex organic chemistry detection using James Webb's enhanced sensitivity might reveal prebiotic compounds consistent with panspermia scenarios or artificial biochemistry signatures, indicating biological cargo. The distinction between natural and artificial organics requires detailed molecular analysis beyond current observational capabilities. The observational outcome tree branches into three primary possibilities based on accumulated evidence patterns. Outcome A describes a natural comet with unusual chemistry that expands our understanding of interstellar object diversity while remaining fundamentally consistent with known physics and formation processes. This scenario would establish 3I-ATLAS as an important calibration point for interstellar object population models, while demonstrating the chemical diversity available through cosmic material exchange processes. The scientific value would prove substantial even without revolutionary implications for life or intelligence. Outcome B encompasses natural seed-like composition that supports Suzanne Falzner's planetary seeding hypothesis, while remaining entirely within natural formation and evolutionary processes. This scenario would provide crucial evidence for cosmic material exchange mechanisms that accelerate planetary formation without requiring biological or technological explanations. The implications for planetary formation theory would prove revolutionary by demonstrating that interstellar objects participate actively in planetary system architecture rather than representing mere curious byproducts of dynamical revive. Evolution. This natural seeding mechanism could explain observed correlations between stellar mass and planetary occurrence frequencies. Outcome C represents the extraordinary possibility of confirmed technological signatures that indicate artificial origin, biological cargo, or engineering capabilities far exceeding human technological development. This scenario carries enormous implications while maintaining extremely low probability based on current evidence patterns. The burden of proof for outcome C remains appropriately high, requiring multiple independent lines of evidence that definitively exclude natural explanations. Single anomalous measurements or ambiguous signatures would prove insufficient for such revolutionary conclusions. The scientific method demands reproducible evidence rather than speculative interpretation of marginal observations. Any confirmed technological signatures would require verification through independent observation campaigns using multiple instruments and analytical techniques. The stakes involved in accurate classification cannot be overstated. False positive declarations of artificial origin would damage scientific credibility for decades, while potentially triggering inappropriate policy responses. False negative conclusions might overlook genuine opportunities for advancing human knowledge about intelligence's cosmic distribution. The next several months will provide unprecedented observational data for testing these competing hypotheses against objective evidence. The instruments stand ready, the coordination protocols are established, and the scientific community awaits results that may reshape our understanding of planetary formation, life's cosmic distribution, or humanity's place within potentially vast networks of galactic intelligence. Part 13. Broader Stakes. If 3I-ATLAS ultimately proves to be a natural comet with unusual chemistry, the most likely outcome based on current evidence, the scientific implications extend far beyond simple classification exercises. We would need to fundamentally recalibrate our understanding of comet diversity, outer stellar system chemistry, and the population statistics that govern interstellar object distributions throughout our galaxy. The carbon dioxide dominance, early water activity, exotic dust properties, and distinctive chemical signatures would establish new categories within comet taxonomy systems developed from solar system examples. This expanded classification framework would better prepare us for the chemical diversity expected from objects formed around different stellar masses, metallicities, and evolutionary histories. Outer system chemistry models would require substantial revision to accommodate the formation conditions necessary for producing 3I-ATLAS's unusual volatile ratios and dust characteristics. The specific stellar environment parameters that enable carbon dioxide-rich comet formation would inform theoretical models of planetary system formation across diverse galactic contexts. Interstellar object population models would gain crucial constraints from detailed analysis of a well-characterized example observed throughout multiple phases of its solar system passage. The size distribution, chemical diversity, and activity level statistics derived from 3I-ATLAS would improve estimates of the total interstellar object population density and encounter rates with planetary systems. These refined population models directly impact planetary formation theory by quantifying the raw material supply available for seeding processes across cosmic timescales. Higher population densities would strengthen arguments for material exchange between stellar systems, while lower densities might support more isolated planetary formation scenarios. If the planet seed hypothesis gains support, whether through 3I-ATLAS serving as a representative example or through broader population studies, the implications for planetary formation theory could prove revolutionary. Strong evidence for Falzner's capture and seeding pathway would establish an entirely new paradigm for rapid core formation that explains observed correlations between stellar mass and giant planet occurrence frequencies. This natural seeding mechanism would resolve the timeline problem that has plagued conventional core accretion theory for decades. The ability to bypass slow dust to planetesimal growth phases through importation of ready-made cores would enable giant planet formation within gas disk lifetimes around stars of all masses. The theoretical framework would also explain the chemical diversity observed in exoplanet atmospheres and bulk compositions. Imported cores carrying chemical signatures from diverse stellar formation environments would produce planetary compositions that exceed the range achievable through purely local formation processes. The seeding hypothesis makes specific predictions about planetary system architectures that become testable through coordination of stellar cluster membership data with exoplanet surveys. Dense, massive stellar clusters should exhibit enhanced giant planet formation efficiency compared to isolated stellar formation environments. Programmatic implications of any confirmed artificial origin would dwarf all natural science outcomes through their impact on planetary defense strategies, SETI research priorities, and international space policy frameworks. First verified extraterrestrial technology would instantly become the most important discovery in human history. Planetary defense protocols would require immediate and fundamental revision to address potential threats or benefits from artificial interstellar objects. Current asteroid and comet deflection techniques assume natural origin objects following predictable gravitational trajectories, assumptions that would become invalid for maneuverable artificial systems. The search for extraterrestrial intelligence would shift focus from passive radio telescope surveys toward active monitoring of anomalous objects within our solar system. The possibility that alien technology routinely transits stellar systems would revolutionize detection strategies and contact protocols. International space policy would face unprecedented challenges in developing appropriate responses to confirmed artificial visitors. Questions of territorial jurisdiction, research access rights, potential communication attempts, and threat assessment would require entirely new diplomatic and legal frameworks. The discovery would also motivate urgent development of dedicated interstellar object interceptor missions based on technologies similar to the European Space Agency's Comet Interceptor concept. Pre-positioned assets in the outer solar system could enable rapid response to newly discovered interstellar visitors, providing close-range analysis capabilities impossible through remote observation alone. Mars-based launch systems might offer optimal platforms for interceptor missions due to lower gravitational escape requirements and favorable orbital mechanics for reaching interstellar trajectories. The development of such capabilities would represent a natural evolution of current Mars exploration infrastructure toward active interstellar object investigation. The data culture benefits from the 3I-ATLAS investigation extend beyond specific scientific discoveries toward improved methodologies for coordinating international observation campaigns and archival data analysis. The coordination protocols developed for this campaign provide templates for future multi-asset observation programs spanning multiple space agencies. Archival recovery efforts using data from surveys like ATLAS Zwicky Transient Facility and Transiting Exoplanet Survey Satellite have demonstrated the value of maintaining comprehensive databases of astronomical observations. These archival searches extend observation baselines and provide crucial constraints on trajectory determination and activity evolution. The rapid international coordination achieved for 3I-ATLAS observations establishes precedents for responding to future discoveries requiring urgent observation campaigns. The communication protocols, data sharing agreements, and joint mission planning procedures developed during this campaign will benefit future interstellar object investigations. European Space Agency and NASA cooperation during the Mars observation phase demonstrates the feasibility of coordinating assets across different space agencies for scientific objectives. This collaboration model could extend to other contexts, requiring rapid response capabilities and international resource sharing. The philosophical implications transcend technical questions about planetary formation or life detection to address fundamental issues about humanity's cosmic context and our species' relationship with potentially vast networks of galactic intelligence or biological distribution. Natural seeding processes would transform our understanding of planetary systems from isolated formation events to collaborative creations involving chemical contributions from across galactic space and time. Earth's materials might include components originally formed around stars that completed their entire life cycles before our Sun began nuclear fusion. This galactic mixing perspective dissolves boundaries between local and foreign chemistry, while establishing complex heritage relationships between worlds, separated by vast distances and temporal scales. Planetary systems become nodes in cosmic recycling, networks that operate across geological timescales. Biological seeding scenarios would establish life's cosmic distribution as a galactic rather than planetary phenomenon. The implications for astrobiology research, life detection strategies, and our understanding of biological evolution would prove profound beyond current scientific frameworks. Artificial origins would confront humanity with evidence of intelligence operating on scales and timelines that dwarf human technological capabilities. The discovery would simultaneously humble human technological achievements while inspiring expanded visions of what intelligence might accomplish across cosmic timescales. The response to confirmed artificial visitors would test humanity's capacity for unified action, careful analysis, and appropriate caution when confronting potentially superior technology. The discovery could catalyze unprecedented international cooperation or exacerbate existing tensions between nations competing for access and advantage. Yet beyond policy implications and scientific discoveries, the investigation of 3I-ATLAS has already demonstrated humanity's remarkable capacity for coordinated curiosity, careful analysis, and open-minded consideration of extraordinary possibilities, while maintaining rigorous standards for evidence evaluation. The process itself, regardless of final conclusions about the object's nature, exemplifies science's ability to transform apparent anomalies into deeper understanding through patient observation, theoretical creativity, and collaborative investigation spanning multiple disciplines and international boundaries. The broader stakes thus extend beyond any single discovery to encompass the advancement of human knowledge, international cooperation, and our species' capacity for confronting cosmic mysteries that challenge fundamental assumptions about our place in the universe. Part 14. The philosophical dimension. The question of whether star systems exist as isolated islands of chemistry or participate in vast galactic gardening networks touches the deepest foundations of how we understand cosmic ecology and our place within it. If interstellar objects routinely ferry materials, organics, or even life itself between stellar systems, the boundaries that define individual worlds begin to blur into collaborative creations spanning light years and geological epochs. This cosmic ecological perspective transforms our understanding of planetary identity from discrete entities to nodes within an interconnected web of chemical and potentially biological exchange. Earth's atmosphere, oceans, and living systems might incorporate materials originally forged in the cores of stars that died billions of years before our Sun ignited nuclear fusion. The implications reach beyond academic astronomy into fundamental questions about origins, heritage, and responsibility that touch every human culture's creation narratives. If worlds grow through galactic collaboration rather than isolated formation, the meaning of home expands to encompass contributions from countless stellar siblings across cosmic history. Origin's humility emerges as perhaps the most profound philosophical consequence of cosmic seeding processes. The assumption that planetary systems represent independent achievements of local physics and chemistry dissolves into recognition that worlds might be co-authored by the galaxy itself through mechanisms operating across scales beyond human comprehension. This perspective places Earth within a cosmic community of mutual dependence and shared heritage that extends our conception of kinship beyond biological boundaries toward geological and astronomical relationships. We become not merely products of terrestrial evolution, but participants in galactic processes that connect our world to star formation regions thousands of light-years distant. The question of what constitutes alive versus lifelike takes on new complexity when considering the possibility that 3I-ATLAS might contain biological materials, biotechnological systems, or autonomous technology that blurs traditional categories. The definitions that separate living organisms from sophisticated machines become increasingly arbitrary as technology approaches biological complexity. Current terrestrial research in synthetic biology, programmable matter, and artificial life already challenges conventional boundaries between biological and technological systems. Materials that grow, reproduce, adapt, and respond to environmental changes might exhibit all functional characteristics of life while remaining fundamentally artificial in origin. Applied to interstellar exploration scenarios, such hybrid systems might enable remarkable capabilities for adaptation, repair, and mission flexibility across the unpredictable conditions encountered during million-year journeys between stars. The distinction between biological and technological becomes less important than the functional requirements for survival and operation. If 3I-ATLAS contains such systems, a possibility unsupported by current evidence, it would represent our first encounter with technology that transcends human conceptual categories for classifying natural versus artificial phenomena. The discovery would force expansion of philosophical frameworks for understanding intelligence, life, and the relationship between them. The Great Silence Paradox, the apparent absence of detectable extraterrestrial intelligence despite the vast scale and age of our galaxy, might find resolution through dark forest. Hypotheses that suggest advanced civilizations practice extreme caution when revealing their existence or capabilities to potentially hostile species. This interpretation suggests that survival in a competitive cosmic environment might require sophisticated camouflage, deception, or misdirection capabilities that render alien technology virtually indistinguishable from natural phenomena. Advanced civilizations might routinely observe younger species while remaining completely undetected through superior concealment technology. The implications for human behavior and messaging ethics become complex when considering whether confirmed detection of camouflaged alien technology should trigger attempts at communication or defensive silence. The response choice could determine our species' survival if the dark forest hypothesis accurately describes galactic power dynamics. Alternatively, the apparent cosmic silence might reflect communication methods, energy scales, or conceptual frameworks that transcend current human technological and intellectual capabilities. What appears to be absence might actually represent ubiquitous presence operating through mechanisms we lack the sophistication to recognize. The philosophical question of prudence versus openness takes on existential significance when confronting possible evidence of extraterrestrial intelligence or technology. The decision to actively pursue contact versus maintaining observational caution could influence humanity's long-term survival and development within a potentially crowded galactic community. Current SETI protocols assume benevolent, or at least neutral intentions from potential alien civilizations, but this assumption might prove catastrophically naive if competitive or hostile intelligences dominate galactic power structures. The detection of camouflaged reconnaissance technology would suggest far more complex and potentially dangerous scenarios. Human narrative frameworks built around assumptions of cosmic isolation would face fundamental revision if 3I-ATLAS or similar objects represent evidence of widespread intelligence or biological distribution throughout the galaxy. Cultural, religious, and philosophical systems would need to accommodate humanity's position as one among potentially millions of intelligent species. The meaning of human achievement, uniqueness, and cosmic significance would require re-examination within contexts where intelligence and life might prove commonplace rather than rare phenomena. This transition could prove either humbling or inspiring depending on how our species chooses to interpret expanded cosmic community membership. Yet the philosophical implications extend beyond simple discovery scenarios toward questions about curiosity, investigation, methodology, and the appropriate balance between skepticism and openness when confronting phenomena that challenge established understanding. The 3I-ATLAS investigation demonstrates humanity's remarkable capacity for simultaneously maintaining rigorous scientific standards while remaining genuinely open to revolutionary possibilities. This intellectual balance represents one of our species' most valuable capabilities for navigating cosmic mysteries that exceed current knowledge frameworks. The process of investigation itself, regardless of ultimate conclusions about the object's nature, exemplifies the philosophical values of collaborative inquiry, evidence-based reasoning, and careful distinction between speculation and substantiated fact. These methodological approaches provide robust foundations for confronting even more extraordinary discoveries that may await us. The philosophical dimension also encompasses questions about responsibility and stewardship that emerge from expanded awareness of cosmic interconnectedness. If worlds throughout the galaxy participate in material exchange networks or deliberate seeding processes, humanity might bear obligations to continue such activities or protect them from disruption. The recognition that Earth's chemical and potentially biological heritage extends across galactic scales creates ethical frameworks that transcend traditional environmental protection concepts toward cosmic ecological responsibility. Our actions might influence not merely terrestrial ecosystems, but galactic-scale processes operating across geological timescales. These expanded responsibility concepts challenge anthropocentric worldviews, while providing inspiring visions of humanity's potential contributions to cosmic evolution and development. Rather than isolated observers of cosmic phenomena, we might serve as active participants in galactic processes that shape planetary formation and biological distribution. The philosophical journey initiated by investigating 3I-ATLAS thus extends far beyond questions about this specific object toward fundamental examination of humanity's cosmic context, our methods for understanding reality, and our obligations within potentially vast networks of intelligence and life that span our galaxy. The investigation process demonstrates that science's greatest value may lie not merely in answering specific questions, but in expanding our capacity for asking better questions, while maintaining both rigorous skepticism and genuine openness to possibilities that transcend current understanding. As we approach our final evaluation of the evidence and competing hypotheses, these philosophical considerations provide essential context for appreciating the stakes involved in determining 3I-ATLAS's true nature and origin. Part 15. Closing speculation. Three roads diverge in the cosmic forest, each leading toward profoundly different implications for humanity's understanding of our place within the galaxy's vast evolutionary processes. The evidence accumulated during months of unprecedented observation campaigns now allows us to evaluate which path best explains the enigmatic visitor we have come to know as 3I-ATLAS. The comet interpretation presents 3I-ATLAS as a chemically unusual but fundamentally natural object that expands our understanding of interstellar visitor diversity while remaining grounded in established physics. This scenario would establish the object as scientifically rich without requiring revolutionary revisions to our understanding of life, intelligence, or cosmic ecology. The carbon dioxide dominance, early water activity, exotic dust properties, and distinctive polarimetry signatures would create new categories within comet classification systems, while demonstrating the chemical diversity achievable through formation around different stellar masses and evolutionary histories. The scientific value would prove substantial through improved models of interstellar object populations and enhanced understanding of outer stellar system chemistry. The artifact interpretation, while lacking supporting evidence in current observations, would represent history's most momentous discovery if confirmed through smoking gun technological signatures. This scenario requires extraordinary proof that current measurements have not provided, but the implications would instantly transform every aspect of human civilization. Confirmed extraterrestrial technology would revolutionize planetary defense strategies, SETI, research priorities, international space policy frameworks, and philosophical understanding of intelligence's cosmic distribution. The discovery would simultaneously humble human technological achievements while inspiring expanded visions of what intelligence might accomplish across galactic timescales. The planet seed interpretation offers a natural mechanism for cosmic material exchange that could revolutionize planetary formation theory without requiring biological or technological explanations. This scenario provides elegant solutions to timeline problems that have plagued conventional core accretion models, while explaining observed correlations between stellar mass and giant planet occurrence frequencies. The seeding framework suggests that planetary systems grow through galactic collaboration rather than isolated formation processes, transforming our understanding of worlds from independent entities to nodes within vast recycling networks, operating across geological timescales. This natural explanation carries revolutionary implications while remaining entirely within established physical principles. The uncertainty inherent in our current knowledge reflects the real-time nature of scientific discovery as it unfolds through careful observation and analysis. The Mars encounter on October 3rd, perihelion passage on October 29th, renewed Earth observations in December, and Jupiter approach on March 16th may provide the decisive evidence needed for definitive classification. Each upcoming observational milestone offers specific capabilities for testing competing hypotheses. Mars-based high-resolution imaging could reveal jet structures, indicating natural outgassing versus artificial control systems. Perihelion monitoring might detect responses to extreme heating that distinguish biological, technological, or purely physical processes. Post-perihelion spectroscopy could document chemical evolution patterns that separate natural volatile processing from managed emission sequences. The Jupiter encounter provides final tests through gravitational physics experiments and high radiation environment exposure that might trigger responses from hypothetical biological or technological components remaining dormant under the normal interstellar conditions. The cumulative evidence from all observation phases will determine which interpretation best fits the accumulated data. We encourage viewers to monitor upcoming data releases from NASA and European Space Agency observation campaigns while watching for specific diagnostic signatures that could distinguish between competing explanations. Isotopic ratios indicating exotic formation environments, non-gravitational accelerations suggesting artificial propulsion, or complex organic signatures hinting at biological cargo would provide crucial evidence for evaluating extraordinary claims. The scientific process demonstrates its greatest strength through the willingness to follow evidence wherever it leads, while maintaining appropriately high standards for extraordinary discoveries. The investigation of 3I-ATLAS exemplifies this balance between genuine openness to revolutionary possibilities and rigorous skepticism that protects against premature conclusions. Yet beyond technical questions about classification and origin, 3I-ATLAS has already succeeded in expanding human perspective about the possibilities hidden within cosmic phenomena that initially appear mundane. The investigation process reveals science's capacity for transforming apparent anomalies into deeper understanding through collaborative inquiry, spanning multiple disciplines and international boundaries. The philosophical implications transcend any specific discovery outcome to encompass fundamental questions about cosmic connectivity, material exchange between worlds, and humanity's position within potentially vast networks of galactic evolution. Whether natural, artificial, or something between these categories, 3I-ATLAS has already challenged assumptions about isolation, uniqueness, and the boundaries that define individual planetary systems. The thought experiment that concludes our investigation asks which discovery would prove most profound for humanity's future development and cosmic understanding. Would learning that we exist within a galaxy, where worlds are routinely seeded through natural processes, fundamentally alter human perspective about our planet's heritage and our obligations to continue cosmic gardening. Activities? Would confirmed observation by extraterrestrial intelligence force immediate revision of every assumption about human uniqueness, cosmic isolation, and the appropriate balance between openness and defensive caution when confronting superior technology? Would discovering that nature operates through mechanisms far stranger and more interconnected than current theories predict prove most inspiring for advancing human knowledge and technological capabilities? Each potential answer carries profound implications for human civilization's trajectory, scientific research priorities, and philosophical frameworks that guide our species' understanding of meaning, purpose, and responsibility within cosmic contexts that exceed individual planetary boundaries. The voting opportunity we present reflects science's democratic character, the recognition that evidence interpretation ultimately depends on human judgment, community evaluation, and collective wisdom that emerges through open dialogue between diverse perspectives and expertise areas. We promise continued coverage keyed to major data releases from Mars observations, perihelion monitoring, post-perihelion spectroscopy, and Jupiter encounter analysis. The scientific story continues evolving as evidence accumulates through the most comprehensive interstellar object investigation ever attempted by human technology and international cooperation. The comments section becomes a forum for community discussion about evidence interpretation, competing hypothesis evaluation, and philosophical implications that extend beyond technical classification questions toward fundamental issues about humanity's cosmic context and our species' relationship with potentially vast networks of galactic intelligence, or biological distribution. Whatever 3I-ATLAS ultimately proves to be, natural comet, artificial probe, biological courier, or planetary seed, it has already demonstrated the universe's capacity for presenting phenomena that exceed our current understanding, while challenging us to develop better questions, improved investigation methods, and expanded conceptual frameworks. The object serves as a reminder that cosmic mysteries await discovery throughout our galaxy's spiral arms, stellar nurseries, and interstellar spaces, where wanderers drift between appointments with destiny that might reshape entire civilizations. The understanding of their place within the cosmic evolutionary process. The investigation continues as 3I-ATLAS journeys toward its appointment with Mars, then the Sun, then Jupiter, carrying within its nucleus whatever secrets first formed around alien stars in distant epochs of galactic history. The answers await those patient enough to follow evidence, while remaining open to possibilities that transcend current human knowledge and imagination. The universe, it seems, still holds surprises for those willing to look closely at visitors from the space between stars.